Welcome to lecture 14. In this lecture, I'm going to talk about manifolds. What are manifolds? There's probably some formal definition of manifolds, but I actually don't know the definition. Instead, what I'll do in this lecture is that I'll give you some examples of manifolds with the idea that you can generalize these examples to get some knowledge of what it is that is meant by the expression manifold. So let's get started. The first example of manifolds I want to discuss is the n-dimensional Euclidean space, which I denote as R to the n, where R here stands for the real numbers and n to the number of dimensions that I consider. The simplest case is the case of 0 dimensions, R to the 0, and that is just a dot. In 1 dimensions, we have R to the 1, so that is basically the real numbers ranging from minus infinity to plus infinity, and we can represent this as a line. In 2 dimensions, we have real numbers that sort of are two-dimensional, and in this case, this generalizes to a plane that I pictorially depict as this symbol here. This notion generalizes to higher dimensions. It's harder to draw like the 3-dimensional version, R3. It will be even harder to do R4 and so on, but you get the idea how a 4-dimensional Euclidean manifold then would look like. The coordinates on Rn would then be coordinates xi ranging from x1 to xn, and the corresponding metric on Rn would be the Kronecker delta, Kronecker symbol delta ij. So that is our first example of manifolds in n dimensions. The second example I'm going to talk about is the sphere in n dimensions, s to the n. In 0 dimensions, we have S0, and not surprisingly, that is exactly the same as we had before. It's a dot, and it's the same as R comma R to the 0, and that just tells you that all 0-dimensional manifolds are just dots. In 1 dimensions, if we want to consider S1, and we get that, we can write this as a circle. So you can see that we get the manifold S1 by taking the manifold R1 and just compactifying the two ends together to form a ring. In 2 dimensions S2, we then go 1 dimension higher, so we get the surface of a sphere here in 2 dimensions. And again, this generalizes to higher dimensions. I should say that there is an Austrian version of S2 that is depicted as this symbol here, and that is known as a Krapfen. It comes in handy in the carnival season in Austria, and it's jam-filled and very tasty. The coordinates on S2 are, for instance, phi and theta, the two angles for the surface of the sphere. And we can write down the metric for these coordinates. The metric is 2-dimensional for S2. It has a radius squared for the radius of the sphere, and then it has it is diagonal, and it has an entry here in the lower right that should be sine square of theta. Apologize for the typo. So this is dependent on the angle. So you can see that this metric here is non-trivial because the space here is curved. There is an obvious generalization of the n-sphere to higher dimensions, Sn, and I want to note that all of these manifolds, all n-dimensional manifolds here are all genus 0, where the genus just tells you how many holes a manifold basically has. To give you a non-trivial example of such a manifold, let me now discuss the n-torus, Tn. In particular, the 2-torus, T2, that basically is a manifold that looks like this. It is a ring and it has a hole in it. Again, you can write this as a manifold, but there's a more interesting version. Let's take the American version of a torus, T2 torus. It's depicted here, very tasty. I don't know whether you know, but it's getting to be lunchtime here pretty soon. Anyways, so this is the American version of a torus in 2 dimensions, and it has genus 1 because it has one hole in the manifold, and that's different from, in particular, the S2, the sphere in 2 dimensions, which had no holes, so that was genus 0. We can always view a torus in n dimensions as a compactification of n-dimensional Euclidean space. And I want to give you a quick idea of how that is done. Let me sort of stop sharing my screen and just show you this. So let's start with a Euclidean manifold in 2 dimensions, which I sort of take to be this paper here. And then what we'll do is we want to compactify some direction here. So for instance, what I do is I'll do a transformation such that two of these ends are going to be on top of each other like this. And then we have compactified one direction of our 2-dimensional space, and we get basically something that is a spherical direction here in one direction, and it's still Euclidean in the other direction. If one goes ahead and then compactifies these two ends, so we basically sort of bends this around. I can try to show this with a slightly more bendable version like this, and I can sort of try to sort of wrap it around such that we get some more or less round shape here. Then we get a torus out of this construction. Never mind my inability to do any actual demonstrations. So that is the idea of compactifying and how to get, in particular, the torus out of a compactification of Rn. I should also say there is the possibility of doing one non-trivial compactification. So I just sort of used periodic boundary conditions. You could in principle add twists to this and get Möbius strips and other things like that. But basically you can always use a torus as some particular compactification of the Euclidean n space. So the way we can get toroidal coordinates, for instance, would be we start with the Euclidean coordinates for R2, x and y, and then we just impose periodic boundary conditions. So we see x is r cosine phi and y is b cosine theta, so that we have two radii for the long radius of the torus and the short radius of the torus, and two angles that describe this. And that's how we would get toroidal coordinates from the compactification of R2. And an associate matrix, of course. Anyways, now let's consider genus 2 surfaces or manifolds. That example that we have is, for instance, double torus or two-holed torus. It sort of looks like this. So it has two holes and sort of is otherwise shaped as two rings glued together. The double torus is genus 2 because it has two holes, so that's obvious. And we can consider further generalizations of this. The next thing that we could discuss is the triple torus. There's a German version of this that looks like this. So it's a pretzel that has 1, 2, 3 holes. And this is an example of a manifold, which is genus 3. There are more complicated versions of manifolds, of course, particularly more complicated versions of two-dimensional manifolds. One of the examples that I want to highlight is the so-called Klein bottle. It looks like this. So basically, it is a two-dimensional non-orientable surface. So you have this picture here where you have this handle of this vase that sort of goes out, comes out here, wraps around, and then is nothing else but the wall of this vase here. So you can fill liquid, for instance, in here. And the interesting thing is that this basically only has one surface. It's just non-orientable as you sort of go around. And you can convince yourself that this is also an example of a genus 2 manifold in 2 dimensions. Okay, why do I tell these stories in a course on general relativity? The relation comes from considering geodesics on manifolds. So recall that a geodesic is the path that takes minimal time to get from A to B. If we sort of say that that is the definition on a manifold, then we have examples. For instance, we have our example for R2 and S2. So basically, if we have here an example for our two-dimensional Euclidean space, if we take the example of 2 points here, A and B, then the geodesic is the path that takes minimal times between these 2 points here, and that is a straight line. Whereas for a sphere S2, the path of minimal time between A and B is not a straight line. It is actually a grand circle that goes along the sphere. And that is basically the solution that comes out from the geodesic equation. Now, with those examples, let me sort of jump to GR and sort of try to do an interpretation of general relativity as a manifold. So just imagine for a moment that our universe is a manifold. Here it's a genus 0 manifold. It's depicted as this funny gridded surface that we have here. And it can in general be curved. Imagine something like an object like the sun deforming this manifold such that it's not R2, but it's some more complicated version of a manifold. And then let's consider geodesic in this manifold. If it was Rn, the Euclidean space, then basically geodesics would be straight lines. But if it is a more complicated manifolds, the geodesic would be curved lines like this solid red line that's depicted here. And essentially the idea is that we can use this as a geometric description of gravity. So if gravity acts in such a way that a gravitational object like the sun deforms the manifold, then the path of a particle, let's take the planet or something like this, or an asteroid, would then no longer be moving on straight lines, but it would be moving along geodesic lines. And if the curvature of this is just right, then we can, for instance, have a closed orbit, which is then a geodesic that goes around in this manifold. So basically, the idea will be that we'll replace the idea of a sort of notion of a force in a flat space-time by the notion of just geodesics in manifolds with curvature. That will be the idea. To close up this lecture, I want to just leave you with some homework assignment, which is that we've discussed several two-dimensional manifolds. We've discussed the S2, which in the Austrian version is this pastry here that doesn't have any holes in it. Then we have discussed the two torus, which in the American version does have one hole in it. We have discussed the triple torus, which in the German version has 3 holes in it. So the homework assignment I have for you is there an edible version of the double torus or the two torus? I don't know the answer to this question, but I would be interested to hear what you find out. And that concludes the present lecture.